Okay. Assalamualaikum warahmatullahi wabarakatuh. Good evening, sir, and thank you for the opportunity to work on the problem after completing the final evaluation of this semester. I will make the best use of this opportunity. So, from the book Introduction to Modeling and Analysis of Stochastic Systems, I decided to work on the problems 4.4 and 4.22, which both are computational problems. So I am Nalini Mahastuti with student ID 157. Okay, for the first problem is 4.4. Actually, to solve this problem, we have to solve number 4.1 first. So this question aims to find what is the probability that the system will last for more than 2 years. Okay, as I said earlier, we have to solve number 4.1 first. In this part, I try to break down what is actually am I supposed to do to solve the question number 4.1. And this is the final answer of 4.1. We got the red matrix and this bunch of informations. Okay, and this is the solution number 4.4. So, indeed, we have to understand those informations that I got from solving number 4.1. So first is a plot failure rate. So the failure rate is 0.2 per year per ton of load. That means the formula is lambda times L per year. And for the total load equals to 18 tons. It's shared equally among 3 cables. That means load per cable is equals to 18 per 3 equals to 6 tons. And the concept of system failure are first, the system will fail if all 3 cables fail, and the cables fail independently of each other. So lambda cable equals to lambda times L equals to 0.2 times 6, and it equals to 1.2 per year. So we have to remember that the aims for this question is to find the probability that the system will last for more than 2 years. Okay, we should understand the concept first. So, probability that the system lasts more than 2 years means that the system won't have any failure. System failure happens if all 3 cables fail. So that means if only 1 or only 2 cables fail, it means that the system not failure. So we have the conclusion here. If probability of a cable lasts more than 2 years is complement of probability of all 3 cables fail. And probability of a cable lasts more than 2 years represents that the system not fail. And the probability of all 3 cables fail represents that the system is fail. Okay, so we have to got both of this probability of the cable lasts more than 2 years, and probability of all 3 cables fail. Okay, first, here, we should get the probability that the single cable lasts more than 2 years, based on the lambda that's exponential distributed. We found the CDF here, and we got that the probability that a single cable lasts more than 2 years was 0.0907. And the probability that all 3 cables fail, and because the cables fail independently of each other, so this is the formula, and we got the probability that all 3 cables fail was 0.7514. Okay, now we could compute the probability that the system lasts more than 2 years. So it equals to 1 minus probability of all 3 fails. and it equals to 0.2486 equals to 24.86%. Okay, for the problem number 2, I decided to solve number 4.22. And this problem also based on the previous problem, um, that was 4.2. But in this case, we only use the rate matrix here. We doesn't need the we doesn't need to compute the transition probability matrix. Okay, so to compute limiting distribution, we have to understand what is the definition of limiting distribution first. So limiting distribution describes the long-term behavior of a Markov chain, and Pi represents the proportion of time the system spends in state I in the long run. And this is the whole concept. Uh, so the limiting distribution for CTMC have two characteristics. First is PR equals to 0, and sum of Pi equals to 1, and must to be 1. And we have to understand this concept too. Rate of exit from state I is the horizontal value RIT in the rate matrix R. And rate of entry into state I is the vertical value RTI in the rate matrix R. So we could get this whole linear equation. So this is for state 1, state 2 until state 6. And this is the final equation that we would use to solve the next step. And this equation we got from these characteristics of limiting distribution of CTMC. So Pi equals to P2 until it equals to P6. Okay, now we go into the second characteristics of limiting distribution of CTMC. That was the sum of Pi have equals to 1. So P1 plus P2 until plus 2 P6 have to equals to 1. So we got P1 equals to 1 per n. And because P1 is equals to another P, so we got that P is equals, and it is 0.1667. So the conclusion is the system spends equal time in each of the 6 states in the long run. Okay, thank you and see you.